Hi. Today we're going to look at a new method of proof, which will be unfamiliar to nearly all of you. It's called proof by induction. When we start looking at it, you will find that it seems rather strange. It seems halfway through as if we're assuming what we try to prove. Well, I'm going to do an example to try and show you what I mean and how this proof by induction is actually a very good and rigorous type of proof. Let's look at this question. Prove by induction that sigma r plus 1 is 1 times 2 plus 2 times 3, etc., up to nn plus 1, that is equal to 1/3 n plus 1, n plus 2. Well, all proofs by induction have a standard way of writing them out. The first thing that we have to do is to make sure that it does actually work for some initial value of n. So we put n equal to 1. If we do that, we get that the left-hand side is equal to the first term, 1 times 2, which is 2. The right-hand side is equal to 1/3. Putting n equal to 1, I get 1 times 2 times 3. That's just 2. And you see now that the left-hand side and the right-hand side are equal, and therefore the formula is true when n equals 1. The next bit is the bit that will seem somewhat strange. Bear with me while I do it, and then I will try to convince you afterwards that it is a rigorous way of proceeding. I am now going to assume that the formula is true. Hey, going around all over the place. The formula is true when n equals some value k. Well, what does that mean? That's telling us basically that sigma 1 to k of r plus 1, that's r equals 1 to k, which is 1 times 2 plus 2 times 3 plus etc., all the way up to k plus 1, is actually equal to 1/3 k plus 1, k plus 2. Right. If that's true, then the next thing we do, we look at sigma r equals 1 to k plus 1. r plus 1. Let's just write out what this is. This is 1 times 2 plus 2 times 3 plus k plus 1. And we're going one term further. That's up to k. We're going up to k plus 1. K plus 1, k plus 1 plus 1 is k plus 2. Now, this is where we're going to use that assumption. The assumption is that 1 times 2 up to k plus 1 is 1/3 k plus 1, k plus 2. In other words, that this first bit is 1/3 k plus 1, k plus 2. That's all the way up to k plus 1. And then we just add the last term, which is k plus 1, k plus 2. Don't multiply it out. There are some common factors, nice common factors around. K plus 1 and k plus 2. So the answer is to factorize. And it's also worth factorizing and losing fractions. So when I factorize this, I will take k plus 1, k plus 2, and 3. Now that's easy to do for the first bracket. if I take the k plus 1, the k plus 2, and the 3, I'm just left with k. This is where, in the second bracket, some of you might like to write 3 over 3. And then, if you take the k plus 1 out, the k plus 2 out, and the 3 on the bottom, you're just left with 3. Oh, and that is exactly what we want. So we have assumed that the formula is true when n is k, some value, and if it's true when n equals k, then it must follow that the formula is true when n equals k plus 1. Okay, now let me try and convince you that we have actually proved something. We showed, or I showed, that the formula was true when n is 1. If the formula is true when n is some number, well, let's say we know that it's true when n is 1. Because it's true when n is 1, it must also be true when n is 1 plus 1, which is 2. Okay, now we know that it's true when n is 2, so it must also be true when n is 3. It's true when n is 3. It must also be true when n is 4, and on and on. So we have actually proved that this formula is true for all numbers 1, 2, 3, 4, 5, 6, and so on. Some people like to write this line as 1/3 of k plus 1 times k plus 1 plus 1, that's k plus 2, and k plus 1 plus 2, that's k plus 3. This emphasizes the fact that the formula is working when n is k plus 1. It is just 1/3 of n plus 1, n plus 2, when n is k plus 1. That is optional. It's a nice thing to do if you like doing it, but that is quite good enough, as I did in blue. One thing that is not optional is what I've written in red. I expect to see n equals 1 and a conclusion that the formula is true when n is 1. You must write that you are assuming that the formula is true when n is k, and after you've done this proof, that it follows that the formula must be true when n is k plus 1. Those are essential parts of your proof. And then finish off your proof with the concluding paragraph, as I've written at the bottom here. So if I can't find the mouse, where is it? I've got it. So your concluding part of the proof is to write out the last paragraph. You've shown it's true when n is 1. If it's true when n is k, also true when n is k plus 1. Therefore, your formula is true for all positive integers n by induction. This and more examples can be found in your textbook FP1 on pages 123 to 127.